Could be more exciting. So Hedera is an emerging public ledger with a set of services described here. It's built on the hashgraph consensus algorithm. So I'll talk about how hashgraph works and how it's different than blockchain and why that gives some arguably interesting features and characteristics. And then I'll talk about Hedera, which is a public ledger built on top of hashgraph, and what notable features and characteristics we think Hedera will provide. So to set the context, this is the sort of application that we think we want to enable and that we believe we can enable. So this is a website, it's live, dailytimestamp.com, with which we're demonstrating the viability of purchasing web content with our native coin, Hbar as we call them, through micropayments, right? The premise is you load this browser extension, it's a Chrome extension, you load it with Hbars from your account, and then you just surf. Right, and based on policies that you've set and preferences and policies over how much you're willing to spend per day, per site, et cetera, you buy the content that you're reading. So rather than signing up for a monthly account and paying a subscription fee, you pay as you go for the web content. So we're not the first to imagine micropayments for web content. But the implication, I think, is interesting because micropayments are only feasible if fees are micro as well. And it's the fact that we will have low fees for transactions pushed to the ledger that will make this feasible. So hashgraph is a consensus algorithm. And the ultimate goal of a consensus algorithm is to allow some network of actors to agree at a given moment in time on the state of some set of business data. That could be crypto balances, or it could be smart contract state. That's what we're trying to achieve. Even under adversarial conditions, right? Where the network isn't reliable, where the actors are not fully reliable, they're both untrustworthy and untrusting. And by definition, the state is changing. So that's the challenge. How do we come to agreement on the state of application data, even under those conditions? For that to happen, if parties are going to agree on the state of some business data, they need to agree on the order of the transactions that change that state. Because only if they can agree on the order will they be guaranteed to stay in sync on the state. And that's what hashgraph is. Hashgraph is an ordering algorithm that allows this community of untrusting actors to agree on a consensus order for the transactions, and notably also agree on a timestamp, a consensus timestamp for each of the transactions amongst all of them. So let's look at how that works. So here's our network, Alice, Bob, and Carol. The goal is for, at a given moment in time, Alice, Bob, and Carol, modulo the fact that one of them might be evil and trying to corrupt the consensus of the other two. How do the honest nodes stay in agreement on the state as transactions happen that will serve to change the state? So these transactions are happening elsewhere and are being submitted to the nodes of the network for ordering an eventual application to the state. So the first step that hashgraph uses is a gossip protocol to allow the fact of each transaction to be distributed amongst the network. So everybody uses a gossip protocol, right? It's fast, it's secure, it's resilient to DDoS. The premise is simple. I've got news to share. I pick another node in the network and I tell them the news I have, and they tell me their news at the same time, because inevitably they know things I don't. So gossip gets the word out exponentially fast to the network, the fact of a transaction happening. So here's Alice, Bob, and Carol just gossiping about these transactions. Inevitably, Alice, Bob, and Carol have a different sense of the order of these transactions because they heard about them at different times, just given the randomness of gossip. And the fact that it was one or the other of them that was first sent that transaction initially. So Alice, Bob, and Carol all have a different sense of what is the best order, the most fitting order for these transactions. They're all different. They all have the same sense of what the transactions are, but a different sense of the order. Our goal is to allow them to agree on an order that is reasonable, right? That all of them think, well, that's not what I would have picked, but I'm okay with it. It's fair. To do that, we're going to leverage a small bit of data that when nodes gossip about those transactions, they add a small bit of metadata, what we call gossip about gossip. Logically, it's just when Alice tells Bob about a transaction, Alice will tell Bob that she heard of it from Carol. So we're talking about the history of gossip. That's the gossip about gossip. It just manifests as hashes that I, as a node, add to my block, a logical block, as in a blockchain. We call them events, but they're containers for transactions. Critically, I don't add a hash to one older event, I add two. So rather than building up a chain, we build up a directed acyclic graph, a DAG. So hash graph is a DAG, one difference from a blockchain. What this gossip about gossip, what these two hashes enable, is that not only do the nodes build up a shared set of transactions, they build up a shared history of what the other nodes know about those transactions, specifically when those other nodes learned of those transactions. So while Alice, Bob, and Carol all have their own sense of the order of the transactions, just by looking at their own local hash graph, they can deduce what the other two know about those transactions, specifically when the others learned of those transactions. So everybody still has a different sense. We haven't yet reached consensus, but at least we have this shared representation that everybody is able to examine and infer and deduce what others know. Still not yet at consensus, though. We just have a shared information set. The next step is to calculate for each transaction, actually for each event, this logical container for transactions, we're going to calculate a consensus timestamp and define it as the median of the times that the community first heard. Is that a question or a scratching head? Okay. So that's how we calculate the consensus timestamp. Everybody looks at their hash graph. Their hash graph, by definition, allows them to know what others or when others first learned of a transaction. And so they can all run this calculation. They can calculate the median just by putting the earliest time first, latest time last, take the middle. Now, we don't allow the whole community necessarily to contribute a time to that calculation, because if we did, then just by going offline, a node could stop us, right? We'd be vulnerable to a malicious node killing liveness. So we actually vote through what we call a virtual voting algorithm. We pick, for a given event, logically a quorum of the full set, a subset of the full set of nodes, and only allow those to contribute a timestamp to the calculation of that median. Critically, it's virtual voting, right? Every every node, again, runs this algorithm looking at their own local hash graph, and they calculate the same quorum as everybody else for a given event. And because they calculate the same voting base, they'll calculate the same median. They don't talk about it. They don't swap ballots over the network saying, well, I think it's, Sunday morning at 11:05. They do it as a local calculation. So that's this local process, this algorithm, virtual voting that each node runs independently. The net result is that every transaction is assigned a timestamp that everybody agrees on. And once you have a timestamp, you can sort them into an order. So we get, from virtual voting, we get a consensus timestamp, then we get a consensus order, and we're almost done. Because now we just simply apply those transactions to the state in the order that we just agreed upon. And critically, every node does that, again, independently. We stay in sync. We started with a shared state. We applied a set of transactions in a consistent order. Everybody comes to the same next shared state. That was the goal. And we repeat. We just keep doing that. It's this iterative process. As transactions happen, they flow into the network. We slot them into this history of messaging. We vote through the virtual voting algorithm to assign them consensus timestamps. Once we've done so, we apply them to state. We move on. Next set. So that's hashgraph in a nutshell. It's this ordering process that has certain characteristics. The first of which is that it's fast. If you think about what I described, the only time we used bandwidth was in the initial gossip phase, when we talked about a transaction happening. And then we added a small bit of overhead through the metadata of the hashes and a timestamp and some signatures. But most of the bandwidth that the algorithm uses is used solely for pushing the transactions themselves. So the algorithm is very efficient in bandwidth. Contrast that with other consensus algorithms where, for instance, transactions flow out to a set of nodes. The miners compete as to who mines the next block, and then those blocks flow back. So to some extent, twice as much consumption of bandwidth. So here are some performance numbers, relatively out of date, and some disclaimers that I'll add. But this shows for varying numbers of nodes, the sorts of latencies and throughput that we can achieve. So hard to read, but the bottom scale tops out at 500,000 TPS. That's with certain assumptions about the numbers of nodes and achievable latency. So the disclaimers here are that this is just consensus. I talked about how we're going to order transactions. These performance numbers don't represent the actual application to state. So for instance, if these were cryptocurrency transfers, Hbar transfers, there would still necessarily be a step where one account was incremented and another decremented. So that's a real effect. The other disclaimer is that these curves are for 128 or 64 nodes distributed across the US. We have other performance curves that show global distribution of the nodes, and laws of physics, the extra network distance means that latency goes up. But this is the sort of scale of TPS that we can achieve. And we're confident that when we go live, we'll be able to support 100,000 TPS for simple micropayments, Hbar transfers. So we're also fair in the sense that there was no leader, no miner, no validator given special permissions, even if only for a short period of time, whether it be 10 minutes or 17 seconds, whatever the block time is. All the nodes were peers in this collaborative calculation of the consensus timestamp. Because there's no leader, even if for a short period of time, there's no opportunity or temptation for that leader to abuse that special privilege, even if only for 10 minutes. So we're not vulnerable to the scenario of leaders, particular miners or block producers, censoring transactions, preventing them being added to consensus, or even just changing their order within the block for nefarious purposes. And because there's no leaders with that ability, there's no need for apps to contemplate that possibility and logically bribe the leader to ensure that their transaction is added to a block. We're also secure. In the first, simplest sense, again, there's no leader means there's no leader to DDoS and take down and thereby prevent consensus. Proof of work has a leader, but it's also resistant to DDoS because the mechanism of electing that leader is sufficiently random that you don't know who to DDoS. But there are other public blockchains where the leader is predictable, sort of a round-robin model. And if you can track the leader, then you can shut down consensus. More interestingly, we're secure because we are asynchronous BFT. So BFT, Byzantine fault tolerant, means that the consensus that we come to has finality. For any one of those nodes, Alice, Bob, and Carol, when they were able to calculate the timestamp for a given transaction, they do so with complete confidence that it will never change, and that the other nodes in the network will also calculate that same value. That's what BFT means. There's finality of consensus. There's no growing sense of confidence and certainty by subsequent blocks. There's finality. And the asynchronous just means that we can achieve this characteristic of consensus even under asynchronous network conditions, without making assumptions about how long it takes messages to flow across the wire. So that's hashgraph. I think I do have an hour. Okay, I'd have to go fast. So that's hashgraph. It's a consensus algorithm. It's an alternative to blockchain with some notable performance and security characteristics, we think. The consensus algorithm itself can be deployed in a permissioned model where the nodes are known and whitelisted to some extent. And that's the business model that we started with, selling hashgraph into enterprises for them to build permissioned consortium ledgers built on hashgraph. CU Ledger is a consortium of 6,000 credit unions that is building out just that ledger, that sort of ledger based on hashgraph for their own financial applications internal to them. But the algorithm itself can be deployed in a permissionless model, one where nodes are not whitelisted. And that's Hedera. That's our emerging public ledger based on hashgraph. It's public permissionless. The caveat here is eventually permissionless. When we launch, it will be permissioned. There will be a set of known nodes, the Alice, Bobs, and Carols, that over time we will open that up to freer participation. It's a proof of stake system. I'll talk about how we use stake to logically weight the votes that I talked about and thereby mitigate Sybil. The governance model is noteworthy and different than the governance models of other public ledgers. I'll talk about why we think that's appropriate. Native crypto, smart contracts, sort of table stakes. The last key feature, for some it's a bug, for us it's a feature, is a licensing model that's designed to inhibit forks. And I'll talk about why we think that's necessary as well. So the governance model for Hedera, it was inspired by Visa of some 50, 60 years ago. The premise is that the collective body that will be entrusted and empowered to make the decisions about how Hedera should evolve will be composed of a council of 39, eventually 39, large-scale, billion-dollar, global, blue-chip companies. Companies with brands that they want to protect, companies with existing businesses that they want to distribute onto a public ledger, global across the world, ultimately every continent represented, distributed across verticals. So it's not just banks, there are banks. It's not just insurance companies, there are insurance companies. There's social media companies. Every conceivable vertical will be represented. The premise and the belief is that this 39, with this competitive dynamic between some of the members, the heterogeneous nature of the members, the fact that we will force renewals through term limits, that this governance model will be more resistant to coercion from governments, more resistant to collusion within council members, just given the nature of the size of these companies. And admittedly, and by design, this is a very different governance model than other public ledgers. We think it's ultimately necessary to bring to a public ledger, particularly if we want to attract enterprise adoption of Hedera, we need to bring this sort of mature, rigorous governance model that enterprises expect. The other notable feature of Hedera is a licensing model that is not open source, or at least not fully open source. Again, the assumption is that for enterprises to be willing to build mission-critical, enterprise-sensitive data applications on a public ledger, they will require that that ledger have predictability and stability. Specifically, they will expect or would hope that that network will not fork with a subsequent creation of a clone to confuse the market, kill any network effect accordingly. I watched yesterday's Bitcoin, battle for Bitcoin, and it struck me that the gentlemen on the stage, all smart, committed people who fully believe in Bitcoin, probably agree with each other on 95% of what Bitcoin should look like. But they disagreed on the 5%, and so we end up with Core, Cash, ABC, SV, etc. We will, as much as possible, try to prevent there being Hedera, Hedera Core, Hedera Lite, Hedera Cash through this licensing model. Now, fully acknowledge that for some, that's anathema to the crypto community, crypto in quotes. But we think it's necessary if the DLT/blockchain technology is ever to reach wide-scale adoption. So it's not open source. Legally and through some technical controls, we will try to prevent that Hedera clone. But it's not to say that we don't acknowledge the value of open source and the power of the sort of transparency that open source review enables. So while the code can't be copied, it'll be open review. So communities who imagine building on Hedera will be able to reassure themselves or assure themselves that there's nothing malicious in the node code. And other aspects of the ecosystem, wallets, SDK, et cetera, those will be open source. Specifically, the code that nodes run won't be. So these are the three platform services that Hedera will launch with. Inevitably, over time, we'll expand this list. We have a cryptocurrency. As I said, we call them Hbars. Because of the speed of hashgraph and the efficiency and bandwidth, the fact there's no proof of work, there's nothing slowing us down, we'll be able to deliver the high TPS that ultimately means we can have low fees. I'll talk about the fee model in a bit. But low fees enable low value transfer. They make possible that, and that's microtransactions or micropayments. Hedera smart contracts, we wrap the EVM. So if a smart contract is running on Ethereum, was written in Solidity, it can be easily ported to Hedera because we logically wrap the EVM. So we inherit the concept of gas as defined in Ethereum, the cost of, or the concept of paying for computation. One difference between how we implement gas and how Ethereum does is that, again, because there is no leader, there is no miner you need to incentivize, preferentially incentivize to take your smart contract call. There's no concept of gas price. Applications don't have to assess how much they want this transaction to be added to a block and preferentially encourage miners to take that. It's flat rate. Another interesting twist is what we call binding arbitration. So when a bytecode, when an Ethereum or when a Solidity bytecode script is uploaded and entered into the ledger, initialized into the ledger, by default, it will have the same immutability guarantee as Ethereum delivers. Specifically, that bytecode will never be changed. If, however, the dev or the admin uploading that bytecode to Ethereum at the time of that initialization wishes to, they can define arbitrators, specifically by listing a set of public keys using M of M logic to stipulate how many of those N need be signing subsequent transactions. What we can do is enable a model of arbitration for any future disagreements over the status of that smart contract. So if you know, in the classic Ethereum example of the DAO, that the DAO could have been resolved if appropriate arbiters, perhaps third parties external to the Ethereum communities themselves, could have determined how to proceed and resolve the issue with the funds that, you know, had been stolen, quote unquote stolen. We also have file storage. So these are files in the loosest sense. We're not storing video files. We're not storing MP3s. We expect small files, hashes of identity claims or hashes of supply chain life cycle moments to be stored on the public ledger. So some business logic happens external to the ledger, and the value proposition is that by recording the fact of that into Hedera as manifested through a hash of some transaction data, you logically establish the provenance of that business data and the provenance of that business process that happened off-chain, because we assign a timestamp to the entry of that file into the ledger. So we have the community asserting that something, as represented by this hash, traceable to some other process off-chain, happened at a given time in history. So, cryptoeconomics for us, 3 aspects. As I said, we're stake-based. Applications pay fees to the network when they submit a transaction, and those fees ultimately fund payments to the nodes that run the consensus algorithm. So stake is necessary to mitigate the chance of a Sybil where somebody spins up 1,000 Hedera nodes and thereby swamps consensus. So it's a relatively simple stake model. The votes that I described earlier when I was describing the hashgraph algorithm are weighted by the stake of the different nodes. So if one node has 1,000 Hbars and another one has 500, the one with the greater number of Hbars that they've logically nominated towards consensus, they have twice the influence toward that calculation of the median, and so the consensus timestamp as the other. What I don't think I display on this slide is that in addition to nodes staking Hbars towards consensus, if you're an account owner who has Hbars but isn't running a node, which clearly there will be for one reason or another, then you can logically delegate or proxy your stake to a node, enhancing their weight and so influence towards consensus, and ultimately receiving a payment in acknowledgement of that boost. The issuance schedule for the coins is designed to either make impossible in the early years or impractical in the later years the possibility of any one actor or some small number of actors reaching 33% of stake. 33% of stake, or 33% of influence more generally, is the absolute threshold for security. We are ABFT modulo no party having 33% of influence. If that happens, then they have full power over the network. They can stop consensus if they were to choose to. So the issuance of Hbars is designed to make that impossible in the early years, because there won't even be 33% of coins in circulation. And then in the later years, hopefully the value of Hbars serve to prevent the likelihood of 33% being possible. Compared to other stake models, it's relatively simple. There's no bonding, there's no loss of liquidity. Any node or an account can logically nominate some number of Hbars towards consensus, but they can spend those nominated coins anytime they wish. Their influence towards consensus will go down, but that's the price they pay for spending. Or if a particular account is nominated as stake, if coins flow into that, their influence goes up. So it's just proportional to how many coins are in that account at a given time. Neither is there any concept of slashing, right? We don't need to punish bad behavior. We just make it impractical modulo the 33%. And it's because there's no slashing that there's no need to bond, right? We don't need to tie up node equity in stake. We just simply measure what nodes have at any given moment in time. So at a high level, what we call proxy staking, that concept of I own Hbars, but I don't wish to run a node. Logically, here's my coins, use them for stake. That feels similar to delegation in DPoS models like EOS. Critically, what's different is that in DPoS, a user's or a coin holder's stake is used to indirectly influence consensus. The model is I'm allowed to vote in a real world election where human actors are picking other human actors, corporations perhaps, and the more stake I have, the more coins I have, the more influence I have towards that election. But the end result of that election is 21 or 100 special block producers. And it's those block producers who are entrusted with subsequently calculating consensus. And we change those, but it's still the stake of the original account holder is used indirectly to influence consensus. In our model, proxy staking, the stake is used to directly influence consensus by directly enhancing the weight of the node in question. So that's stake. Another aspect of the economics are the fees that clients pay to, logically, the network when they submit a transaction. So again, similar to Ethereum in that clients, when submitting an application, will look at a fee schedule, look at the actual characteristics of their application, and determine what is the appropriate fee for that transaction. Now, transactions by definition are gossiped and entered into consensus. Queries are not. Queries are just a logical account balance lookup or something comparable. How big is this file? What's the balance in this ERC20 contract? So queries aren't as expensive. But the premise is that the transaction fees should reflect the different characteristics of the transaction. Specifically, how big the file is if you're uploading a file, how long you expect to store it on the ledger. You'll pay more if you store it for a month than if you do a week. So that's the concept of rent that Ethereum is recognizing now, I think, that they need to better acknowledge. And again, comparable to gas, the processing burden that a given transaction will place on the nodes in the network. So the fee model, again, is that I'm assembling a transaction and I'm going to submit it to one of the nodes, Alice, Bob, or Carol in our example. Based on a published fee schedule, the application will calculate what is the required fee for that transaction, stipulate that it is willing to pay that fee, and submit it to the network. The other nodes validate that that fee is sufficient based on their understanding of the appropriate fee, and if so, they'll process it, add it into consensus, and ultimately apply to stake, or to state. Now, the fees that clients pay, some aspects of those go directly to the first node that facilitated the submission into the network. Other aspects are collected by the Hedera treasury account, and then on a daily cycle, fund payments out to the nodes of the network, logically paying for the work they've just done for the past 24 hours. Not only do nodes get this daily paycheck, but account holders who proxy to nodes also get a similar payment. Probably proportionally less because they probably staked less than the node, but they're still compensated. So logically, 24 hours, every 24 hours, at a given moment in time, payments flow from the treasury account out to the community to compensate them for the costs associated with running a node, bandwidth, CPU, et cetera, but also give them a reward. We want nodes to think of this as a profitable exercise. So it's not just covering your costs, but making it worth your while. So here's a representative slice of some of the dApps that have announced they're building on Hedera. That's all I have for content. Happy to take any questions. I'm sorry, I didn't hear. Can you speak up? So the question is, or the assertion is that the gentleman has heard that we are inherently interoperable, which sounds like a good thing. It sounds like a good thing. So I suspect that they might be talking about the portability of Ethereum Solidity scripts from Ethereum to Hedera. We have, other than that, I don't think we have anything special to promise with respect to interoperability, other than perhaps the fact that because we're BFT, interoperability across chains becomes a simpler proposition, because within a chain you can reach certainty. I'm not sure what they would be speculating about. Thank you very much.